Hey guys, so my internet dropped in the middle of our lecture, so I'm going to try to go over some of this again real quickly to pick up where we are, and then continue on in the lecture. So I apologize if you were watching live and you got dropped or whatever. I don't know what was happening on your end, but I think we're back. Okay. So we're looking at an introduction to polynomial equations and graphs. All right. And so the first thing we need to know is what a polynomial is. And the easiest way to see that is through examples. So for example, here I have f of x, g of x, h of x, and k of x are all different examples of polynomials. And what that means is just a bunch of terms added together where we have x to some positive exponent or a constant. Okay, so for example, f of x, 3x to the fourth plus 11x squared minus 2x plus 10 is a polynomial because it's just a bunch of terms added together with positive exponents. Okay, and then my constant here. H of x is one that maybe you don't think about much, but it is a polynomial. H of x equals 4. A constant is a polynomial, so we're okay with that. And k of x is something that kind of is going to be useful to us. If I can factor a polynomial, then the factors, I still have a polynomial, I've just changed the way it looks. And remember, factoring turns an addition statement, which would be like the polynomial written out at the beginning, like f of x, into a multiplication statement. And the multiplication statement is the multiplication of a bunch of simpler polynomials. So factoring helps us take complicated polynomials, break them down into easier polynomials to work with. All right, now here's a more formal definition of a polynomial. It's an expression of the form p of x, and we just write this out. The reason I have this a sub n x to the n power plus a sub n minus 1 x to the n minus 1 power is that I can assign the coefficient with a label that we call an index. And so a sub 3, for example, is a coefficient to x to the third power. And that's just a mathematical tool because this definition, this p of x here I've written, covers every single polynomial ever thought about. And I did it in one statement. So it's a more precise way of defining it, even though it's a little bit confusing to see. All right, now what I want you to get out of this is that the degree is n. So the highest exponent is what I call my degree. And a sub n is my leading coefficient. So the coefficient of the highest term is my leading coefficient. Okay? All right, now another term associated with this is a root or a zero. And we'll use those terms interchangeably. Sometimes we say solution, and sometimes I may even say the word factor. And what it is it's a value that makes the polynomial equal 0. So when I plug this value into the polynomial, I get 0. All right, now if you think about it, and where have we seen that in the past with graphs? If I let y equal 0 and solve for x, I'm finding my x-intercepts. And so in a graph setting, the 0 is the x-intercepts. All right. And again, you just need to think of the 0 as it's not 0 itself, it's the values that make the polynomial equal to 0. Okay, sometimes that is 0. So the example I had here before everything kind of went wonky on me was that I have a polynomial p of x. I want to verify that x equals 1 is a 0. So 1 is a 0. For this polynomial, yes, it is. And so notice I have p of x equals x minus 1 times x squared plus 2x plus 5. And if I plug in the value 1 in for x, I get 1 minus 1, which is 0, times 1 squared minus 2 times 1 plus 5, which becomes 4. 0 times 4 is 0. So when I plug in the value 1, I get an output of 0. That means x equals 1 is a 0, or an x-intercept for this polynomial. I believe we are now caught up. I hope that makes sense. Okay, now what we are going to do is we're going to look at how to graph factored polynomials, and we'll use Desmos to help us with that. And hopefully that makes sense, or hopefully it will make sense. Okay, so we're graphing polynomials. And let's say we're graphing factored polynomials. The reason we want to graph the factored polynomials is because, I mean, look at the example we just did. it was obvious to me that x equals 1 was a 0. Why? Because I had this x minus 1 as a factor. And when I set it equal to 0, I could just say, well, let's take a look. If I had said x minus 1 times x squared plus 2x plus 5 equals 0, then I know, if I'm solving this as an equation, that x minus 1 equals 0, and, or I should say, or x squared plus 2x plus 5 equals 0. And in this case, we only needed to solve for x equals 1 to find that that was a 0. If I factored x squared plus 2x plus 5, and I could do that through maybe completing the square or the quadratic formula, I'm going to get some more zeros. Possibly, if they're real numbers, they may be complex. Okay, so that's why we want to graph factored polynomials, is because once it's factored, we can easily find the x-intercepts. And so there's two big things we need to graph factored polynomials. One, we need to find what we call the end behavior. Secondly, we need to find our zeros, or our x-intercepts. And when it comes to factored polynomials, that's pretty easy to do. And we should also add, let's say, zeros with multiplicities. And I'll explain what that means in a little bit. Okay, so let's first look at end behavior and see how the end behavior affects our graph. Okay, so we're now looking at end behavior. And let me get a graph here. I'm just going to make up a graph, something like this. And a polynomial function will graph something like that. Okay, now the end behavior is talking about what's going on as x gets incredibly large, either in the positive or the negative direction. Okay, so this is saying what happens to the graph as x goes to infinity or as x goes to negative infinity. What happens as x, and we write it like this with an arrow, as x approaches infinity or x approaches negative infinity, so going out that way. That's what the end behavior is talking about. And so in this particular graph, notice, right, so infinity is out this way, right, and negative infinity is over here. So as I'm going this way, as I'm going out towards positive infinity, what is the graph doing? Is the graph kind of, sometimes it'll just maybe approach a line like x equals 0, y equals 0, like a horizontal line. In this case though, notice that the further I get out this way, the further down my graph is going. And we write it like this. So as x approaches infinity, my function that I guess we'll call f of x here, f of x just keeps going down, right? That's going to be approaches negative infinity, and that's what we call the right behavior, because that's what's going on the right. Okay, now on the left, so on the left behavior, what is going on? So as x goes out this way towards negative infinity, what is my graph doing? As x is going out towards negative infinity, well, look at the graph. It just keeps going up, right? So here we can say as x approaches negative infinity, my function will approach positive infinity, and that's what the left behavior is doing. Let me say it again. As x goes out to negative infinity, my function's going to just keep going up. And so that's what we mean by left behavior, and right behavior is kind of what's going out on the ends. All right, now, for functions in general, you need to approach this using techniques we learn in calculus. But with polynomials, we don't need to do that. We can just learn some simple rules, because there's something that's very easy that dictates what goes on here, okay? So let me set this up for a second. Okay, so there's two things to keep in mind. So let's let p of x be a polynomial, and we need a degree and we need a leading coefficient for this polynomial, but we want to stay general. So let's say with degree n, so n is the degree. I'll highlight that with a different color, and leading coefficient, let's just call it a. All right, so the leading coefficient's a, n is my degree. All right, now what happens? Then the end behavior, we can do it this way. Let's break it up into two cases. So first, I'm going to let n be odd, and then we're going to let n be even. Okay, and then we also want how about a positive and a negative. All right, so here we're saying, look, we have some sort of polynomial. The leading coefficient is either positive or negative, and the degree is either odd or even. Okay. Now for the right behavior, so now we're going to look at right and left in each of these cases. And don't worry, you're going to see that it's actually pretty easy to keep up with. Okay, if the leading coefficient is positive, so let's think like x cubed, then what happens is as I go out to the right, my function's always going to go up. Okay, so I'm just going to write up. But by up we mean as x goes infinity, f of x also goes to infinity. That's what we mean by up. As x goes infinity, f of x is going to positive infinity, it's going up. Okay? Now for the odd case, going out to the left is going to do the opposite of what happens on the right. So in the left, we're going to go down. For even case, for n even, think about a parabola like x squared. What happens? It goes up on both sides, right? It's going to follow exactly what happens on the right. So if n's even, the left and right are going to be the same. If they're odd, they're going to be opposites. Okay, now what happens when a is negative? The leading coefficient's negative. So think about x squared. Now think about negative x squared. What happens? The negative x squared gets flipped upside down. So going out to the right, I'm actually down. And since in the odd case, remember they do opposites, so the left will be up. So where I had this, now you multiply it by -1, you get this. Okay, on the right, they do the same thing. I'm sorry, when n is even, the right and the left are the same. So if a is negative, they both go down. X squared, negative x squared, like that. Okay, so this little chart characterizes the end behavior of polynomials. Okay. Let's do an example. We're going to graph, let's just find the end behavior for right now. And then what we want to do eventually is just be able to graph a polynomial. All right, so let's figure that out. But first, let's find end behavior of, how about f of x equals, I don't know, -3x to the 7th plus 11x minus 2. Okay, I don't know a lot about -3x to the 7th plus 11x minus 2, but I think I can find the end behavior here. All right, so let's start off by figuring out the degree. So my degree here is the highest exponent, which is 7, and the leading coefficient will be the coefficient of that term. So the leading coefficient here is -3. All right, so what that means here is that the degree is odd and the leading coefficient is negative. I know exactly what's going on then. So on the left, we'll start out on the right, right? On the right, since I have a leading coefficient that is negative, instead of going up, I'm going to go down. And since it's odd, so on the left, since it's odd, what happens? The left and the right are different. So the left, it's going up. So what do I know about this polynomial? I don't know a lot, but I do know that this graph, eventually, it's going to do like this. On that side, it's going to do like that. And on the left, it's going to go up like that. And what I don't know is what happens in the middle. Okay, but for right now, all I know is what's going out on the extremes, right? When x goes to positive and negative infinity, it's going to go down on one side, up on the other. Does that make sense? Okay, so that's the first big concept we need to graph a factored polynomial. What's the second one? We need to be able to find the zeros and their multiplicities. Okay, and I'm going to try to explain what we mean by multiplicities. Let me find an example here. Alright, so we're going to move on to the zeros. And multiplicities. Okay, so now let's factor, so let's let p of x, our polynomial, be a factored polynomial like this. Let's say x minus k1 times x minus k2 cubed times x minus k3, something like that. Okay? Let's say k3 the fourth. Alright, now, here are my zeros then. From that polynomial, I can tell you my zeros. I can tell you my zeros from the way it's factored. Remember, if I set this thing equal to 0, I know that k1 is a 0, I know k2 is a 0, and I know k3 is a 0. Those are my factors of this polynomial. Now the multiplicities, what does that mean? The multiplicity is the number of times that factor shows up in the factoring. So for example, x minus k1 was a factor to the first power. It was only there once, so its multiplicity is 1. But k2 is not only a 0 one time, it's actually a 0 that shows up 3 times. Okay, and then k3 also had a multiplicity of 4. So you can see that from these exponents here, right? Those are your multiplicities. Okay, and actually the zeros tell us what? That the graph is going to hit the x-axis at those points. What does the multiplicity tell you? They actually tell you something too. So odd multiplicities, the graph will pass through the axis at that point. So here at k1 and k2, the graph is going to pass through the x-axis like this. Okay. What about even multiplicities? Because I can't figure out what else could happen. So an even multiplicity, all right, the graph is going to bounce at that point. Another way of saying this, and this is a mathematical term, it kisses the axis. So it hits the axis and then bounce off. And that's what we mean by an even multiplicity. Okay? So here k3 is an even multiplicity. I know the graph there is going to bounce. So let's just make up an example. Let's put in our k1. Let's say k1's there, k2's there, and k3 is there. I don't know a lot about this graph. I mean, I don't know anything about, well, actually, I could figure out its behavior if I wanted to, but for the time being, let's not worry about that. Okay? But I do know that I have an odd multiplicity at k1 and k2. So the graph's going to do something like this. It's going to pass through at k1. It's going to pass through at k2. But at k3, it's got an even multiplicity. So when it hits k3, it's going to hit and bounce. So it's going to be something like that. And I might have this thing upside down. I think I probably do. But that doesn't really matter. All I'm trying to show is how the multiplicities and the zeros tells us how the middle laces up. And with that, I believe we are now ready to try to graph a polynomial. All right, and we can check ourselves if we need to on Desmos. Okay, so this is actually example 2 from the textbook, and it says graph the following. All right, let's start with A. We have negative x times 2x plus 1. Whoops, I got a little ahead of myself there. Let's say we have f of x equals negative x times 2x plus 1 times x minus 2. And I want to sketch a graph of this. Okay, so we need to do a couple things. First of all, we need to find the behavior, and then we need to find the intercepts. And actually, for this one, my x-intercepts are easier to find than my behavior because it's already factored for me. Okay, and we're actually going to find the x-intercepts with the multiplicities. Okay, so here I have, since it's already factored, I can just set this thing equal to 0 and solve for each factor. So I see I have from here, I have an x-intercept at 0. The multiplicity is 1. All right, from this middle part, 2x plus 1 equals 0. If you need to, you can say 2x plus 1 equals 0. That means 2x equals negative 1, or x equals negative 1/2. There I get a 0 at negative 1/2, and it has a multiplicity of 1, right? These are all actually to the first power here. All right, the third one, x minus 2, I get x equals 2 as a 0, and it has multiplicity of 1 as well. So what I know about my graph at this point, here's what I know. I know that I'm going to have intercepts at 2, 0, and negative 1/2. I have intercepts at those three locations, and I also know because of the multiplicities being odd that the graph is going to pass through at those three places. Okay, good. Now we need to find our behavior. Okay, now from this one, since it's factored already, I kind of have to imagine if I FOILed out everything. Because that's going to help me figure out my degree and my leading coefficient. So if I FOILed out all this stuff, the first term is going to look like, well, if you FOILed all this out, you're going to have a negative 2x cubed plus, well, I don't really care what everything else is. Okay, that's going to be my highest term, right? Because I just took a negative x times the 2x times the x to give me negative x cubed, negative 2x cubed, plus whatever else happens, but I can't get higher than x cubed, right? So here, I hope that makes sense, and I'm kind of multiplying it out, but I don't really need all the details. I just need the first term. So from that, I can see that my degree here is 3, and my leading coefficient is negative 2, which is in fact negative. Okay, so that tells me some stuff. What does it tell me? So from the leading coefficient, I know that on the right, since I have a negative leading coefficient, as I'm going out to infinity, I'm going to be going down, my function is going to be going down to negative infinity, so my right behavior is down. And I know so on the left, is it down or up? Well, I have a degree 3 polynomial, and remember for odd degrees, they go different directions, right? So on the left, I'm actually going up. All right, so now I can sketch a graph, I think, of my polynomial, because I know on the right, so as I'm going out this way, it's going to be going down somewhere, and as I'm going out this way, I'm going to go up, okay? And I know from my multiplicities that I'm crossing the x-axis at every time. I think then I can put it together. Let me do a new graph just for your notes so it makes sense here. So I have, here's negative 1/2, here's 0, and here's 2. All right, I'm passing through it those three places. I have a in behavior going down. I think it's going to go something like this. It's going to go up somewhere, hit 0, passes through, right? It passes through at all three zeros. And then notice my left behavior is up, which is exactly what I thought. Okay, I hope that makes sense. Let me quickly go over one more example. And I was planning on double checking this with Desmos, but I think for the sake of time, since we had some technical issues at the beginning, I'm just going to go past that for right now. This is correct. All right, trust me, it's correct. All right, so let's look at, this is part C in the textbook. H of x equals x to the fourth minus 1. Okay, for this situation, I believe it's the fastest to start out with the in behavior. Why? Because it's not factored for me already. So I'm going to look at behavior first. And if it's multiplied out already, I know the degree, I can easily see that to be 4. And I can easily see the leading coefficient, since it's just x to the fourth power, is going to be 1. Okay, so that tells me then, on the right, since I have a positive leading coefficient, I am going up. And on the left, since I have an even degree, what do even degree polynomials do with their behavior? They go in the same direction, right? They either go both down or both up. In this case, then, they're both going up. Okay, now what about the intercepts? So let's look at the x-intercepts. I need to then set this thing equal to 0. And what I'm going to do is I'm going to factor, because I recognize that this is x squared squared minus 1 squared. So I can apply the difference of squares here and end up with x squared minus 1 times x squared plus 1 equals 0. And the x squared minus 1 factors to give me x plus 1 times x minus 1. And the x squared plus 1 doesn't factor over the real numbers. What you end up with now, if I set these three things equal to 0, I end up with x equals negative 1, positive 1. And then if you want to think about this, x squared equals negative 1, what does that? Plus or minus I. So as far as x-intercepts go, I only need to consider negative 1 and 1, right? The i's aren't going to show up in my graph. And all my multiplicities are 1 here. Multiplicities, 1 for everything, because every factor showed up only one time. Okay, so now I believe I can graph this thing. Let's see, let's do it right here. I have, again, let's think, I have x-intercepts at negative 1 and positive 1. Multiplicities of 1 in both directions, so it's just going to pass through. I have the right and in behavior, right and left in behaviors are both up. So it's going to do something like this. And in the middle, if you wanted to, you could figure out your y-intercept just to help get a good picture. Y-intercept would be you let x be 0. So I get 0 minus 1, which is negative 1. So my y-intercept is down here. Let's see, at negative 1. And so it's just going to kind of go through like that. Which makes sense. I mean, think about this graph. We just talked about last section, you take x to the fourth, which is a parabola looking thing that bends at 1. And then the minus 1 is what? A vertical translation down 1 unit, right? That's what is happening to this h of x. I take the x to the fourth function and just shift it down 1. And look at the graph I did here. That's exactly what I did. And the way I figured it out was just from a different method. I looked at the intercepts by setting it equal to 0 and got these two intercepts. And then I looked at the in behavior. Again, since it was an even degree, they're going to end up in both directions. And since the leading coefficient is positive, the right's going to be up. Therefore, the left is up as well. And the result is the exact same as if we had just taken x to the fourth and moved it down 1. Okay? I hope this makes sense. All right, I'm sorry that we had some issues at the beginning. We'll try to clarify that or get it cleared up next time. Hopefully the internet will be stronger. If you have any questions for me, let me know. I'll be glad to help. And we'll see you later, guys. Thanks for watching.